This chapter sets a foundation for the study of linear regression, one of the most basic and widely used statistical models. Before studying regression, we must understand the concept of how and to what degree two variables may be related to another. And here we're going to focus on linear relationships. Concepts we'll cover in this chapter: the difference between explanatory and response variables. We'll study scatter plots as a way to display the relationship between two variables. We'll interpret scatter plots, add categorical variables to scatter plots, measure the linear association between two variables using what's called correlation, and discuss some of the facts about correlation. To begin with, suppose we want to know, does more hours of study lead to higher grades? Do heavier cars have fewer deaths than lighter cars? Do shorter women have a higher risk of heart attack than taller women? In all these cases, we're asking, is there a relationship between two quantitative variables? So we have two variables. The response variable measures the outcome. So for the example of more study time and higher grades, the response variable, the outcome, is higher grades. The explanatory variable may help to explain or influence changes in the response variable. So the amount of studying helps to explain grades. So here's an example. Does the amount a person smoke influence or help to explain his or her life expectancy? Or does a person's life expectancy, how long he or she lives, explain or determine how much a person smokes? Well, obviously, it's the first case. There's a clear distinction between explanatory and response variable. The amount a person smokes influences his or her life expectancy. On the other hand, does a person's weight explain how tall a person is? Or does a person's height explain how much a person weighs? These two variables are related to each other, but there isn't one that's clearly an explanatory or response variable. Note, we often want to know if changes in one variable causes changes in a response variable. We can't assume this to be true, even if two variables are related. For example, ice cream sales and drowning deaths are very closely related. As one variable increases, the other variable increases also. So we could say that they're strongly related, but certainly we're not going to say that ice cream sales cause drowning or the other way around. The most useful graph for displaying the relationship between two quantitative variables is called a scatter plot. A scatter plot shows the relationship between the variables measured on the same individuals. The values of one variable appear on the horizontal axis, and the values of the other variable appear on the vertical axis. Each individual in the data appears as a point on the graph. So, to make a scatter plot, we decide which variable should go on each axis. If a distinction exists, then we plot the explanatory variable on the x-axis and the response variable on the y-axis. Always label and scale the axes, and then plot the individual data values. Remember, data come in ordered pairs. For example, the local ice cream shop keeps track of how much ice cream they sell versus the noon temperature on that day. Here are the figures for the last 9 days. A scatter plot. The explanatory variable, the temperature, we can determine ahead of time and say that temperature probably helps to explain ice cream sales. So that goes on the horizontal axis, on the x-axis. The response variable, the amount of ice cream sales, goes on the vertical axis, on the y-axis. A single data point is made up of two values, an ordered pair here. So this point, for example, 15.5 degrees and $332. Those two go together. To interpret a scatter plot, we follow the basic strategy of data analysis from chapters 1 and 2. We look for patterns and important departures from those patterns. As in any graph of data, look for the overall pattern and for any departures from the pattern. We can describe the overall pattern of a scatter plot by the direction, form, and strength of the relationship. An important kind of departure is an outlier, and that's an individual that falls outside the overall pattern of the relationship. Two variables have a positive association when above average values of one tend to accompany above average values of the other. Two variables have a negative association when above average values of one tend to accompany below average values of the other. We might also say that as one variable increases, the other variable increases. That's a positive association. Or as one variable increases, the other variable decreases is a negative association. So how do we interpret this? Well, there's a moderately strong positive linear relationship between temperature and ice cream sales. Note, we have here the strength we describe as moderately strong, the direction is positive, and the form is linear. It appears that higher temperatures mean higher ice cream sales. Note, there's one possible outlier. The temperature of 22.6 appears to have a lower than expected sales of ice cream. Now, consider the relationship between mean SAT mathematics scores and percent of high school graduates taking SAT for that state, for each state. Here we have a nice little scatter plot. If we separate the states by region, we might be able to see a hidden pattern. So here we are adding a categorical variable, namely the region. So if we separate these into red and blue data points as those that are eastern states versus all the others, it's fairly clear to see that there's a cluster of eastern states at the high end of percent of grads taking the SAT, whereas the cluster of the red tend to fall into the lower percentages of graduates taking the SAT. Now, one way that we can determine the strength and direction is to use what's called the correlation. The correlation R measures the strength of the linear relationship between two quantitative variables. It's given by this formula. Notice the formula, after the summation sign sigma, we have x minus x bar over the standard deviation. That's a z-score. And next to it we have y minus y bar over the standard deviation, another z-score. So essentially we're looking for departures from in the x direction from the mean and in the y direction from its mean. R is always a number between -1 and 1. R greater than 0 indicates a positive association. R less than 0 indicates a negative association. Values of R near 0 indicate a very weak linear relationship. The strength of the linear relationship increases as R moves away from 0 and toward -1 or 1. The extreme values R equals -1 and R equal 1 occur only in the case of a perfect linear relationship, when the data points are exactly on. Here are some scatter plots along with their correlations. In the upper left, there is essentially no correlation between the two variables. It's as if we could just throw darts at a board. In the second case, there is a weak negative correlation. As the x variable increases, the y variable tends to decrease. But it's a weak relationship. In the third panel at the top, the third scatter plot, the correlation 0.5 is becoming moderately strong. We can sort of clearly see an increase from left to right. The correlation in the next panel at the lower left there's a stronger association between the variables in a negative direction. So it begins in the upper left and falls toward the lower right. The next panel, correlation of about 0.9, we can almost begin to see a clear linear relationship between the two variables. The points are beginning to look like they fall very near a straight line. And then the last one, r equal negative 0.99, it seems almost clear that the data points fall almost exactly on a line. And in this case, the line is, again, falling from upper left to lower right. There's a strong negative association. Generally, we talk about a weak relationship, a moderate relationship, or a strong relationship. And those are somewhat subjective terms. Positive R indicates positive association. Negative R indicates negative association. The correlation is always a number between -1 and 1. The closer the R value is to 0, the weaker the relationship. If R equals 0, that means there's no relationship. As R increases toward 1 or -1, that indicates a stronger linear relationship. There are some cautions here. Correlation requires that both variables be quantitative. Correlation does not describe curve relationships between variables, no matter how strong the relationship might be. Correlation is strictly for linear. Correlation is also not resistant. R is strongly affected by outlying observations, just as the mean and the standard deviation were. All right, let's take a look at a couple of examples here. So here we have boats registered in Florida versus manatees killed by boats. Seems clear there's a fairly strong relationship. It's a positive linear relationship. As the number of boats registered increase, the number of manatees killed by boats also increase. In the second, we have the number of storms predicted versus the number of storms actually observed. There is a moderate linear relationship. Again, as one variable increases, the other tends to increase. It's not as strong a linear relationship as the manatee example was. So we can say that storm predictions and versus observed are moderately related. If we have, for example, here the healing rate of a limb for a particular animal versus the healing rate of another limb on the same animal, we see that the variables the points are scattered about a little bit more. It's rather difficult to distinguish whether there is any kind of a linear relationship. So we would say that that's probably a weak relationship. So basically what we can conclude is that the healing rate of one limb really has no effect or bearing or doesn't help to explain the healing rate of another limb, or at least not strongly so. In the last case, we have last year's percentage return for particular stocks versus this year's percent return. Here, these are essentially random dots. Correlation is very near 0. And the interpretation here is that while we'd like it to be predictable, the percentage of returns that we got last year doesn't have any association or relationship with the returns this year. So last year's can't help us to predict what's going to happen next. So to review, we talked about explanatory and response variables. We can construct and interpret scatter plots, add a categorical variable, calculate and interpret correlation, and describe some of the facts about correlation.